do today is to consider the following issues. We're going to consider how to find horizontal and vertical tangents on our implicitly defined curves. And we're also going to consider the very interesting issue of phantom points. And to get there, what I'd like to do is to consider the curve x cubed y squared plus x squared y cubed is equal to 36.
This still uses implicit differentiation.
Yes, definitely. And you can see that because I've got x's and y's, yep, and y is not an explicit function of x. So the first thing that I'd like for you to do is for all of you to go to Wolfram Alpha and go ahead and get a graph of this thing so that we can see it. Phantom points. Sorry. Here we go. Phantom points, points that are not actually there on Jeff.
So,
Isn't this like a
what
whole?
does that mean, like,
You'll see. Go ahead and get a sketch of this based upon what you see in Wolfram Alpha. Sketch that into your notes. I'll do my version right here so we can all see it. Isn't this thing beauteous?
Yes.
is there a way to graph these on your own graph calculator?
Not unless you can solve for y equals f of x. Ah, standard computation time exceeded. There it is. Maybe it's because we all did it at once.
Yeah, mine doesn't work again.
It's really odd. Try refreshing it in just a minute. So we can see the graph right here. Obviously, the graph is really sort of weird. And what we are trying for now is to find horizontal and vertical tangents. And just looking at the graph, my eye scans this thing and I see really only one place where we have a horizontal tangent, and that's going to be right here. Does everybody agree with that? And everywhere else, my tangent line is not going to be exactly horizontal, although I do notice that my tangent lines get flatter and flatter as x goes out to infinity. And as far as vertical tangents go, it looks to me like I've only got one place where I have a vertical tangent as well, and that looks to be right there. Although I do notice that my tangent lines get steeper and steeper as x gets close to 0. So what I'm trying to do now is to analytically find these horizontal and vertical tangents. And for that, I need, of course, dy dx. So back to our thing right here. Excuse me. We're going to need to find dy dx. I'd like for all of you at this time to use implicit differentiation to find dy dx. Go. By the way, how many of you did get a graph and how many of you did not get a graph? Yes, got a graph? And how many of you did not get a graph?
Oh, I did not.
What are your?
Was that the same yesterday? Yes. You did not get a graph yesterday?
I did.
That's so weird. Did you try it at home? And the same thing? With your iPad and their website. Which kind of iPad do you have?
iPad Air 2.
iPad Air 2. How about you?
Whatever the school gave me.
So it'd be an iPad 2, but not an Air.
And
you have enough many, I see. Yours is new. And yours worked fine, right? Luke, you got a graph? And so we start here, like this. And on the left-hand side, we get 0. Right-hand side, we get 0. On the left-hand side, we have to remember what? Product rule. If we forget product rule, we're going to do silly stuff. So please notice that I have the product of x cubed y squared in the original, so I have to remember the product rule. First times the derivative of the second plus the second times the derivative of the first. And then for the next term, product again. So that I get first times the derivative of the second plus second times the derivative of the first. And then all of that equals 0. Now, sometimes students at this point will get confused about the algebra, but the algebra is always exactly the same because what we will have here is a certain number of terms that are multiplied by dy dx as a result of the chain rule. Please notice that you will not ever get anything other than dy dx to the first power as a result of chain rule. If you find yourself with an expression like dy dx squared, or the sine of dy dx, or the square root of e to the dy dx, you've done it wrong. The only way to get the dy dx here is from the derivative of the inside, and that's by multiplication times the derivative of the inside. So, we're going to end up with certain terms here and here that are multiplied by dy dx. And we will have certain other terms that are not multiplied by dy dx. And we're going to take the terms that are not multiplied by dy dx and bring them to one side by subtraction. So this term right here becomes negative 3x squared y squared. And this term right here becomes negative 2xy cubed on that side. And on this side, we have 2x cubed y dy dx plus 3x squared y squared dy dx. So what I've done is now to move all the terms without dy dx to one side by subtraction from both sides. And I've kept all my terms with dy dx on this side. Is everybody good with the algebra so far? And now factoring is your friend. Out comes a factor of dy dx. And we divide. Well, I'm getting ahead of myself. The hardest part about this is that you have so many x's and y's floating around that it's really easy to dork up and just drop something. You know what I'm saying? It's just easy to write it wrong. And I just did that right there. I wrote 2y cubed before I caught myself real fast. So you got to watch and slow down and make sure that you've done what you wanted to do. Let me just do that here, and here, and here, and here. And there. Okay? Are we good? Yes.
Second to last row where it has, where it has 2x squared y squared.
Uh-huh.
Y squared.
That was this term right here. Yep. And now we're ready for the big division. dy dx equals all of this divided by all of that. A little bit challenging, definitely a skill you want to practice several times so that you can do it without having to think about it too much. Now, how does that help us in our goal? Here it is. We're going to have horizontal tangents when dy dx is equal to 0. And we're going to have vertical tangents when dy dx is infinite. That's it. Yeah. Plus or minus infinity. Okay? Now, question. Do you think it's worth trying to simplify the top and the bottom at all? I think it probably is. And here's why. Because I am trying to find where the top is 0 and the bottom is 0, it makes sense to me to make those as small as possible before I go solving for solutions.
Could you factor out?
Yeah, what factors do you see, common factors?
You could do x, y.
Yeah, that's right. So I could factor out an x, y, and when I do, I lose a factor of x and a factor of y in each term there. Divided by, lose a factor of x and a factor of y in each term there. And now that's a little bit nicer. Okay, so under what circumstances will this dy dx be equal to 0? Answer, when the numerator is 0. So dy dx equals 0 when negative 3xy minus 2y squared is equal to 0. And so this now allows me to solve this equation right here. But something really interesting happens. How am I going to solve it? Well, factoring is my friend, right? So I'm going to solve it by factoring. What factors do you see? I see a y. I see a 2y. I see a negative 2y. And when I factor out a negative 2y, what is left behind?
X minus y.
Not x minus y. I factored out that negative 2 equals 0. So this now gives me
Isn't it negative 3x?
yes. You're right. I copied it wrong. Different derivatives, same strategy. Factoring. What do you see now?
Which is negative 1 y.
Negative y. Leaving me with what?
Wait, how can I
Well, I have a negative 1 in each.
Oh,
Yeah.
oh, I was looking for the copy.
And leaving me with what?
3x is 2 plus
3x plus 2y. That's exactly. Now, we're going to solve this using our zero product property. If I multiply two things together and get 0, one of them
is 0.
has to be 0. So either negative y is equal to 0, or 3x plus 2y has to be equal to 0. Well, the y equals 0 part I understand pretty well. This part is very interesting because what it gives me now is a relationship between x and y. It does not give me a value for x, it does not give me a value of y, but it does tell me that y is going to be equal to negative 3/2 of x. Does everybody see the algebra part? Now what does this mean? Let's go back to our graph. Going back to our graph here, this is telling me that my points of horizontal tangency are either going to lie on the line y equals 0, or they are going to lie on the line y equals negative 3/2 x. I do not yet know what the x value is, so I'm going to have to come back and plug in for x for y in order to determine those x values. Does that make sense? So the analysis of setting dy dx equal to 0, because my dy dx is defined implicitly, does not give me a specific xy pair. It only gives me some additional information. How am I going to actually find the values of x and y? Well, if I go all the way back to where I started, I began with a relationship that constrains x and y. So that if I happen to know that y is equal to 0, or if I happen to know that y is equal to negative 3 halves x, I can now substitute in here and find a value for x or for y. You see what I'm saying? Yes? No? Kind of? Let's do it. Keep in mind that x cubed y squared plus x squared y cubed is equal to 36. And now let's take that and combine that with the information that we have found for our horizontal tangents. Yep. And plug in y equals 0. And plug in y equals negative 3 halves x. When I plug in y equals 0, I find something really disturbing. What do I find?
0 is 36.
I find that 0 is equal to 36. On what planet does 0 equal 36? No planet whatsoever. What does this mean? This means that the point where y equals 0 is a phantom point. It's not actually on the graph.
What does that mean?
That means that although my dy dx analysis gave me y equals 0, there isn't actually a point on the graph where y equals 0. And therefore, this corresponds to a spurious solution. I got a solution, but it's not really a solution because it's not actually on the graph. It actually corresponds to something else that I'll show you in just a second. Heidi's question, what does that mean, is a good one. But let's try the other one and see if it gives us something a little better. What if y equals negative 3 halves x? Now I can plug in y equals negative 3 halves x, and I find something. I find that 9/4 x to the 5th plus, actually minus, 27/8 x to the 5th is equal to 36. And that looks a little grotesque, but I can clear the fractions by multiplying both sides by 8. And when I multiply both sides by 8, I get 36 times 8 over here. I'm not going to simplify that yet. I may not need to. And over here, when I do, I get 18x to the 5th minus 27x to the 5th. What is 18x to the 5th minus 27x to the 5th? Negative 9x to the 5th. And hey, I can solve this equation pretty easily by dividing both sides by negative 9. And when I do, don't reach for that calculator. What is 36 divided by negative 9? Negative 4 times 8 is negative 32. And therefore, x is equal to negative 2. And if x is equal to negative 2, keep in mind that y was negative 3 halves x to begin with, right? So therefore, y is equal to positive 3. And we have located a point of horizontal tangency at the point negative 2, 3. This was detailed, but it wasn't hard, right? I had to set dy dx equal to 0. And when I did, I got some relations that I could then substitute back into the original to find the actual point that we were talking about. In one case, I just got a phantom point. There was no point where y equals 0. In the other case, I got a real point. And that is my point of horizontal tangency. Yes?
What is the point of horizontal tangency?
Because dy dx at that point is 0. The slope of the line tangent is 0. Let's go back to the graph and see what happened with respect to these 2 points. Do you remember how I said that we had 2 different relations, and one of those relations gave us y equals negative 3 halves x, and my point of horizontal tangency had to lie on that line. Well, take a look at what we found. Look at that point. What's its x coordinate? Negative 2. What's its y coordinate? Positive 3. There is my point of horizontal tangency. Right on the line y equals negative 3 halves x, where our analysis promised it would be. What about the point y equals, on the line y equals 0? There isn't a point. However, Heidi, there is some meaning to it. What do you notice about my graph as we head out towards infinity? What's its horizontal asymptote?
0.
Y, not 0, but
Y.
y equals 0. The y equals 0 here actually was telling us something. It was saying that we have a slope that is approaching 0 as x goes out to infinity. My dy dx is approaching 0 as x goes out to infinity.
So that means
That's what the phantom point corresponds to.
Okay.
That's right.
So does that mean if it was set to equal negative 36, it would approach 0 if we went out to negative infinity?
No. That means if your equation had originally been x cubed y squared minus x squared y cubed equals 36.
No, I mean,
You would get that.
yeah.
Replace x with negative x, and that's what you have. Yes?
Phantom points are always horizontal asymptotes?
That's a good question. That's your best bet. But I don't have a proof for it. My intuition is yes.
Definitional.
Yeah. Sorry.
Is there a definition for
Phantom point. We're just using that to describe a point that does not actually exist on the graph. So we got a result from the dy dx equals 0. And then when we followed that up by substituting here, the point wasn't actually on the graph. So we call that a phantom point. But it's not a math term. I'm just using that term to describe.
Wait, so it's not a math.
It's not an official math term. So.
Oh.
Yeah. Okay, well, what about vertical tangents? Well, we had to do a lot of hard work here, but the vertical tangents are going to greatly resemble that. Here's the one difference. A vertical tangent is a place where dy dx is infinite, and that's going to occur when the denominator is equal to 0, when I end up dividing by 0 in dy dx. So I use the same kind of reasoning here. Let me take that denominator and copy it. 2x squared plus 3xy. Equals 0 means that dy dx will blow up. And so the same sort of thing will happen. Tell me how the analysis goes. Start me off, Emily. No, I'm just saying solve this equation for me. Okay.
Are you? I'm confused about what we're trying to do.
Well, I've got an equation, 2x squared plus 3xy equals 0, and now I need some solutions for that equation. The best I can do.
Okay, so we're just starting kind of from what we had.
Yeah.
Okay, so then you would find the derivative.
Solving doesn't really involve finding derivatives. She needs a tool for solving.
Graphic.
Unfortunately, not very graphable. Could do if you rearranged it a little bit. She needs an F word. Factoring is your friend. Yes, that needs to be a line of first resort, and if I ask you to solve it, even if you don't know how to solve it, just start factoring if you can.
Just factor. So you're taking x out.
Right.
And then it would be 2x plus 3y equals 3.
All right, and what conclusions can you draw from this factorization?
X equals 3.
4.
Y equals negative 3. Y equals 2x, or 2x over 3.
Yeah, negative 13. All right, so this has the same meaning as the previous thing. We've got two possible candidates here. One is that my vertical tangent will lie on the line x equals 0. The other is that it will lie on the line y equals negative 2x plus 3. So we're going to follow up each one of those by substituting into the original in order to get a solution. So I go back to my original, x squared y cubed plus x cubed y squared equals 36. And I substitute x equals 0. Would you look at that? What happened? We have a phantom point. That's exactly right. So we have no solution there.
Oh.
Or I can substitute now y equals negative 2/3 x, and when I substitute y equals negative 2/3 x into my original relation, then I discover that negative 8x to the 5th over 9, no, over 27, plus 4x to the 5th over 9 is equal to 36. And once again, I can solve by clearing the fractions. What should I multiply both sides by? 27, that's right. I'm going to multiply both sides by 27. Then I get negative 8x to the 5th plus 3 times 4 is 12x to the 5th is equal to 36 times 27. I don't feel like multiplying that out just yet. Let's see what happens. What is negative x to the negative 8x to the 5th plus? That's right. And what is 36 divided by 4? 9. And 9 times 27, don't work too hard at this. 9 is 3 to what power? 3 squared. And all right, and 27 is 3 to what power? 3. So I've got 3 squared times 3 to the 3rd, which is the same as 3 to the 5th power. And so x is 3. Yes, this was a little bit of a contrived example. And if x is 3, y is negative 2/3 x, which is going to be equal to negative 2. Again, this took some patience, right? But it wasn't actually hard. It just took some patience.
Mr. King,
Yes, ma'am.
above the top.
Yeah.
What was the dy dx negative infinity?
Oh,
What is that?
so we were looking for vertical tangents on a
Oh,
graph.
I thought that part was confusing me.
Okay, well, vertical tangents, actually, let's go to our graph to see what we're looking at. Vertical tangents are going to be places where my derivative is infinite because my tangent line has to have an infinite rate of change at that point. And so for that reason, dy dx has to be infinity, which means the denominator of dy dx must be 0.
Okay.
So we took that denominator, set it equal to 0, and there it was. And when we did, we found two solutions. One was the vertical line x equals 0. Hey, look at that. Another asymptote. And the other one was y equals negative 2/3 x, which is this line right here, and it intersects the curve right at that point. Okay?
Okay.
Sir?
Will the asymptotes that we find from the parameters always be at 0?
No, not necessarily. I could have, in another equation, gotten x equals 3 or something like that. Plugged that back in and found out that 12 equals square root 6. And then that would tell me how to. If you have an equation with no solution, then you have no point on the graph that goes out. Good. Any other questions? I want to very quickly address something that shows up occasionally, and that is to find the second derivative of an implicit function. It's not hard, but if we go back to the first curve that we had the other day, x squared plus y squared equals 25. And we now ask this question, find the second derivative. Then we're going to have to do it in stages. First, we're going to have to find dy dx, and then we're going to have to find the derivative of that. So, you know how this goes. We take the derivative with respect to x on both sides. We get 0 over here. We get 2x plus 2y dy dx over here. And with a little bit of algebra, we find out that dy dx equals negative x over y. And we're all pretty happy with that, right? The second derivative is just the derivative of that. So, we can do that. But we now have quotient rule, low d high, less high d low. All lower denominators squared. And this gives me y times -1 plus x times, notice I've got dy dx again here. Oh, that over 1 squared. This is a perfectly correct answer, however, it has a problem. And the problem is that it has 3 different quantities in it. It has a y, no problem there. It has an x, no problem there. And it also has dy dx in it. That's a problem. Because dy dx is not a part of the original problem. My original problem has only x's and y's. So I need to replace dy dx with what it is. What is dy dx? Negative x over y. So that this is really my second derivative right here. It's kind of ugly. Sue just made a face. And I agree with her. This is kind of ugly. And so we might want to clean it up. Here is the second wrinkle that happens. Can you close the door? The second wrinkle that happens is that when you go simplifying, a lot of times these second derivatives will boil down into something much, much smaller. So while this is an acceptable answer, no problem with it, when you look in the back of the book, you're not going to see that. Let me show you what happens. First of all, I can simplify by clearing the fractions, right? Multiply top and bottom by y. And when I multiply the top and bottom by y, then I get, in the first term, negative y squared. In the second term, negative x squared. In the bottom, I get y cubed. Everybody take a look at that and make sure you're happy. But now here's the next wrinkle. You look in the back of the book, and the back of the book says this. And you go, what? Where'd that come from? And you go, did I do it wrong? No, I didn't do it wrong.
Y squared minus x squared.
And then you go back, oh yeah, x squared plus y squared was 25 all along. So they just factored out a -1 and got negative 25 over y cubed. Until you see somebody else do that, who may not be as brilliant as all that, But once you've seen it a couple of times, and the way that you'll see it is you'll get an answer, you'll look in the back of the book, and it's much simpler than yours, and kind of look at it and go, did they substitute somewhere? And then you'll start to see opportunities here. This is good for your algebra, like broccoli. So look for opportunities to substitute. Do not be deterred if your second derivatives have a different form from the back of the book. Don't wave the white flag until you try to substitute.